All right, welcome. Today, we're going to tear apart a really fascinating coding problem. Now, on the surface, it looks super simple, but hiding just underneath is a classic trap that gets a lot of people, and a seriously elegant solution that's going to add a powerful new trick to your own problem-solving toolkit. Okay, you ready? Let's get into it. So just take a look at this question. It's pretty direct, right? We've got a list of numbers, and for each one, you just have to look at all the numbers that come after it and count how many are smaller. Seems easy enough, but how would you actually write the code for that?
Let's make this real with an example. This is the count of smaller numbers after self problem. So if our input is 5, 2, 6, 1, the answer we're looking for is 2, 1, 1, 0. But why? Well, let's break it down. For the first number, 5, you look to its right. You see 2, 6, and 1. Out of those, which ones are smaller than 5? That's 2 and 1. So we have 2 of them, and our first answer is 2. Make sense? Okay, next up is 2. To its right are 6 and 1. Only 1 is smaller, so the answer is 1. For 6, only 1 is to its right and smaller, so that's another 1. And finally, for the number 1, well, there's nothing to its right, so the count is just 0.
Okay, so the most obvious way to solve this, and probably what you're thinking right now, is what we call the brute force approach. It's exactly what we just did in our heads, right? For each number, you just loop through everything after it. But this simple path, well, it leads straight into a trap. Here's exactly how that logic would work for our first number, 5. We start with 5. Then we look at the next number, 2. Is 5 bigger than 2? Yep, so our count is now 1. Next, is 5 bigger than 6? Nope, count stays at 1. Last one, is 5 bigger than 1? Yes, it is, so our count goes up to 2. And we're done for the number 5. Now you just have to do that whole process again for every other number in the list.
And this is the trap. This whole method works great for a tiny list of 4 numbers. But the real problem says the list can have up to 100,000 numbers. Think about that. A loop inside another loop on a list that big, you're talking about billions, maybe even trillions of comparisons. That is way, way too slow. You're going to hit submit, and boom, time limit exceeded. So this is the real challenge. We need a much smarter way.
And that smarter way, it comes from a complete shift in how we look at the problem. Instead of looking forward from the beginning of the list, we're going to find the answer by looking backward from the end. This is the big idea. This is the insight that unlocks the whole thing.
So let's ask ourselves that exact question. What happens if we just flip it? What if we process the list from the last element all the way to the first? How does that change what we know at each step of the way?
You see, when you think forwards, it's like for every number, you have to look into this unknown future to find your answer. But when you think backward, the problem totally flips on its head. As we process each number from the right, we can add it to a history of numbers we've already seen. And the question becomes so much simpler. It's not, what's coming up? It's, of the numbers I've already dealt with, how many are smaller than me right now?
Now this backwards approach is brilliant, but it does create a new challenge for us. We need a really efficient way to keep track of this history of numbers, and a way to ask questions about it really, really fast. We need a special tool for this job.
So this completely reframes our goal. We need a data structure that can do 2 things very, very quickly. First, let us add a new number to our history, and second, instantly tell us how many numbers already in that history are smaller than the new one we're looking at.
And that perfect tool for the job is called a binary index tree, or a bit for short. Now, don't get hung up on the name. It sounds way more complex than it is. For our purposes today, all you got to know is that a bit is like a magic black box that is amazing at doing exactly those 2 things we need, updating a value and querying for a count. And it does them in what's called logarithmic time, which is just ridiculously fast.
Okay, there's just one tiny setup step we need before we can use our new tool. You see, binary index trees like to work with a nice clean range of positive numbers, but our input numbers could be huge or tiny or even negative. The solution is a clever little trick called discretization. We just map our unique numbers to simple ranks, starting from 1.
Here's how that works with our example. We take our input 5, 2, 6, 1. Then we find all the unique values and sort them. That gives us 1, 2, 5, and 6. Now we just assign ranks. The smallest number, 1, gets rank 1. The next one, 2, gets rank 2. 5 gets rank 3, and 6 gets rank 4. See? Now, instead of dealing with these random numbers, our bit gets to work with this clean, compact set of ranks from 1 to 4.
All right, the moment of truth. We have our backwards insight, we have our super tool, the binary index tree, and we have our rank numbers all ready to go.
So let's put it all together and watch this solution build our final answer one step at a time.
Okay, let's really focus on this table. We are moving backwards, remember? So we start with the very last number, 1. Its rank is 1. We ask our BIT, hey, how many numbers have you seen so far with a rank less than 1? Well, we just started, so the answer is none, 0. We record that 0 as our first result. Then we update the BIT to say, okay, now I've seen a number with rank 1. Cool, moving on, backwards. Next up is 6. Its rank is 4. We ask the BIT, how many numbers have you seen with a rank less than 4? The BIT checks its history and says, well, I've only seen one that fits, rank 1. So the answer is 1. We record it, and then we update the BIT with rank 4. Now for the number 2. Its rank is 2. The question is, how many numbers have a rank less than 2? Again, the BIT has only seen rank 1 that's smaller. The answer is 1. We record it, and we update the BIT with rank 2. And finally, we process our first number, 5. Its rank is 3. We ask, how many numbers have a rank less than 3? The BIT looks and has seen ranks 1 and 2. So the answer is 2. We record that, and we're done. The results we got backwards are 0, 1, 1, 2. We just have to reverse that list to match the original order, and what do we get? Our final correct answer, 2, 1, 1, 0.
So look at what we just did. By combining these ideas, we took a problem that looked like it would be a total brute force nightmare, and we turned it into something incredibly elegant and efficient. Let's recap the powerful strategies we just put in our algorithmic toolkit. First, and this is the big one, don't ever be afraid to change your perspective. Processing a problem backwards can sometimes turn a really complex, I need to see the future problem into a simple, I just need to remember the past problem. Second, discretization. It's such a great trick for cleaning up messy, real-world numbers into a format that these advanced data structures love. And third, know the right tool for the job. Something like a binary index tree for fast updates and queries, it's an absolute game changer.
And it's worth pointing out, the real hero of this story is the backwards insight. The binary index tree is just one tool you could use to pull it off. You could get the same super fast result using other structures, like segment trees, or even by cleverly twisting a merge sort algorithm. The big idea is always more important than the specific tool you use.
And that leaves us with one final thought. We just saw how flipping a problem completely on its head changed everything. So the question I have for you is this. What other complex problems that you've run into might have a surprisingly simple solution if you just tried starting from the end?